Welcome. This is my first visit to GTU, and it's a great pleasure. And I already met some of you in yesterday or today. So let me introduce myself. My name is Feng. I'm from University of Oklahoma in Norman. I'd like to share with you this afternoon is some of my recent research, and this is to do with EHD-Enhanced heat and mass transfer. And so first, you may wonder, what is EHD? Okay, what is EHD? So EHD is the abbreviation, so it's an abbreviation for electrohydrodynamics. Okay, so E, H, and D. And so from the name, you know that this is a subject, okay, dealing with the electrical field, okay. And so basic is the electrical field and the fluid mechanics, hydrodynamics. So we say the EHD is the study of this motion of an ionized particle and their interaction, when they interact with the electrical field and the surrounding fluids, okay? And so this is the EHD. So in general, we say that this phenomenon is related to the conversion of energy, because basically we use the electrical energy, to drive the flow field. So it's a direct energy conversion. Through this EHD, and we can use to enhance heat and mass transfer. And the mechanism is so-called this secondary flow, and also known as the coronal wind or ionic wind. So I explained it how we generalize this secondary flow. And I know that some of you already familiar with the corona, right? So corona is something that you probably observe that sometime in the humid humid day, okay, before the storm, and if you look at the transformer, then sometimes you can see the glow, okay, over the transformer, and that is corona. And the corona was first observed, you probably from the history, is that is a sailor, okay, on the sea when the storm coming, and they see this glow on their ship, and so that's. So earlier, people don't know what's this. Okay, they were afraid of this, but this is basically electrostatic phenomena, right? And so how do we create this corona wind? So to create this corona wind, we need to have two electrodes. Okay, so one electrode, okay, have to charge at the high voltage, and the other electrode have to ground it. So there will be this potential difference. Okay, and so when we charge this electrode, the so-called emitting electrode at a high voltage, okay? And so if the air in between, so the air will be ionized, because this high electrical field going to break up the neutral air, so into this ion pair. And then because of if it's the same polarity, right? So then this ion, okay, if in this case, if this emitting electrode is charged at positive voltage, so the positive ion will be repelled from this end, right? So we'll toward this the grounded surface or this grounded electrode. So during the transition, so this ion will collide with the neutral electron, okay, neutral molecule, and break up, and so create additional. So this mechanism and continue. So because of this, so we create a wind, and so we can see that the corona wind, you can think about is a jet, it's a microjet issue from this emitting electrode to the grounded electrode, okay. And because we create this jet, and it can be used to this, say for example, this for enhanced heat and mass transfer. There are many applications for this EHD technique, and probably most well-known application is used for electrostatic precipitation. Okay, so for example, that you want to clean the air. Okay, and this has been used in industry. For example, the power plant, coal-fired power plant. When you burn the coal and you have this emission of this particulate matter, and you want to get rid of this. So what we do is provide this high voltage here, okay, to the electrode. And so when the dusty air pass through this electrode, and so the dust, okay, or this solid particle will be charged. And then there's a grounded electrode or another electron here, so it will be deposited. The particle will be deposited to this, and then the clean air can be released. And so in a power plant, then there will be a mechanism to shape this electrode and collect the dust. Okay, so this is the most well-known application for electrical field. And it can also use to control the boundary layer. Okay, so we know that flow over this, say for example, airfoil. It depends on the velocity. Okay, so there will be a separation of boundary layer, and the separation of boundary layer going to increase the drag force. All right. So if we want to reduce the drag force, then we can attach the electrode over the airfoil. Okay, and so in that case we can delay the separation, and so because of this, then we can reduce the drag force. And so it can be also used to enhance heat transfer, because it creates a jet, so it creates this jet impingement. And so here I'll show you a video later. So for example, here you have this computer chip, right? And so it generates heat. And you want to have this doing the thermal management, so we can use this device, okay, create this jet, and so take out the heat. Okay, so this is the use for heat transfer enhancement. And similarly, because the similarity between heat and the mass transfer, so we can use the same thing for drying. So drying basically take out the moisture. Say for example, if we want to dry the agricultural product, okay, so we can use this corona wind. And this has a very distinct advantage, because corona wind is generated at atmospheric pressure and is at the room temperature. And so particularly good for drying, okay, for those material which is heat sensitive, okay, and because of this, so agricultural product is good, because if you use a traditional drying method using the thermal drying, then many times you're going to destroy some of the nutrition in the agricultural product. And many research already found that using corona wind drying, using this EHD-Enhanced drying, it can preserve the nutrition, it can preserve the color, and also sometimes preserve the taste. Okay, and so this is something that which is have been gaining attention. And the other is used for gas pumping. Okay, so gas pumping is that of course, if you want to dry the floor, you can use a fan or pump. Okay, in this case, using EHD is very attractive. Okay, because you can see that there's no moving part. Okay, basically you just create this two electrode and then apply voltage, then you can create this flow. Another reason, another application have been just getting attention is they call it plasma medicine. Have you seen the TV show or movie Star Trek? Right? So Star Trek, you can see that in the movie, the doctor. Okay, when they want to heal people, he got some device, right? And you can see he has a beam, okay, and then you can heal this wound. And that is not a fiction now, because they have been studied using corona, okay, And because the corona it creates this ion that it has many components, and people start realize that some of this ion actually is very good to heal wound. And several years ago, one of the doctors want to prove this is the case. So he cut his finger, okay, and then applied it, and he showed it next day the wound healed, okay. And so it has been gaining this attention, and not just heal the wound, it also have this cosmetic effect, okay. People in Korea, you probably know Korean, they are very, they are quite advanced in these cosmetic things, and they use this thing for teeth whitening, and it also prove effective. So anyway, that's something I just want to let you know. It has several applications beyond our imagination, okay? And so to do this, we had to have 2 electrodes. And these 2 electrodes had to have a different curvature, okay? So usually, one had to have large this radial curvature than the other, okay? And so to do this, then we can see that the factor related to this discharge, okay? So the shape of the electrode is critical, and the electrode polarity is important, and also this electrode spacing, okay? Ambient condition, okay? These are all come to play. And in my work, okay, I usually restrict it to using this DC, okay, direct current, okay, but it can also apply to AC. And if you understand well the phenomena of the DC, then of course extend it to AC is not a problem. So when we apply this positive polarity, we see very different physical characteristics. Okay, so if we apply the positive corona, then we can see the corona glow is very uniform, very stable. Okay, but if we do the negative one, that we will find that the discharge is more unstable and is non-uniform. Okay, typically we can create this corona discharge either using this needle, okay, and using the plate. And because a needle, you can see that have a very small radial curvature, and the plate has an infinitely large radial curvature. So it had to be very different, okay? Or we can use the wire. So wire going this way, perpendicular to the plane, and this is a plate. And so the way it creates this corona width also very different. So you can see if we use the needle, the corona we create is more like a round jet, okay? But if we use this wire, so you can see the wire goes this way, so it is similar like a slot jet. Okay, so that's the difference. So if needle electrode, so you can see it's a 3-dimensional round jet. Okay, and if we create this using a wire, it creates this slot jet. So here I want to show, let you see, okay, what kind this this corona looks like. Okay, so here, this is a video that we took in drawing experiment. So here we have the weighted material, and we use a three needle, okay? And so in this video I'm going to show is that I'm going to increase the voltage from corona onset voltage all the way to we call the spark over. So spark over voltage is when the voltage is very high, and it break all this air in between. And so it basically create the lightning. Okay, so you can say it's a lightning phenomenon in the lab. Okay, that's called a spark over. And then I'm going to reduce the voltage. So we're going through a cycle. So there you see this thing. So this is spark over. You can see the sort of lightning. Okay, you can see that. And now reduce the voltage. Okay. And then I'm going to turn the light off so you can see the in the dark what it looks like. So this is for the positive. Okay, so you can see the glow. Okay, and this is when the charge at the negative. Okay, So nakedly usually is more unstable, but in here you can see that the voltage is different. So it seems like it is kind of steady, but if you apply the wire, then you can see the glow, okay, moving along the wire. All right, so what are the advantages using this technique? As I mentioned, the first thing is simple, very simple. There's nothing, not complicated, okay? And there's no moving part. That's the most important thing, okay? And another advantage is a very low power consumption, okay? So we need to have a very high voltage to create this corona, but the current involved is very small. So the power, the voltage times the current is very small. And so usually we are looking at like less than watt, okay, most application. And this thing can be improved, okay. For example, I'm interested in this EHD is because when we apply to MEMS, okay, there's a MEMS device. In the MEMS device, the order scale been reduced. When you reduce the scale, so that means you reduce the spacing between the electrode. If you reduce the spacing between electrode, you don't really need a high voltage because to create a corona is the electrical field. Okay, so electrical field base is a voltage divided by the distance. So you reduce the distance, then the required voltage proportionally reduce. So when you apply this micros device, okay, you don't need to go to a high voltage. So you can create this win, particularly say we want to create this design a lab on chip. Okay, you want to devise this simple the thing and do the analysis. Okay, and then you don't need to have a pump or fan because at such a small scale it's not practical to use a mechanical fan. Okay. And because it's all controlled by electrical field, so we can control the performance by adjusting the electrical field. So it's very easy to control. And when you apply to drying, so you can see this is a basic, is very suitable for low temperature application. So corona is also called a low temperature plasma. Because usually you want to create a plasma, you have to apply the high temperature, okay? But in this case, it's a low temperature plasma. But EHD is not all this advantage. It has some disadvantage, okay? And one of the disadvantage is that we cannot apply it to all kinds of working fluids. We can only apply it to dielectric. So the fluids cannot be conducted, okay? So it had to be dielectric, okay? So air will be good, okay? Or the gases will be good. And if we want to apply a liquid, so it had to be, say for example, transformer oil, okay? It's not something that can conduct electricity, okay? And it requires high voltage, but then this, we can relax this requirement because, as I mentioned, really depend on the spacing. So if the spacing reduced, then high voltage requirement can be relaxed. Unfortunately, when we apply high voltage, it usually will create ozone. Okay, ozone will generate in this high voltage application. But the ozone is not good for human health, okay? But we studied, we found that the ozone generation, okay, ozone is a very active agent, okay? And so as long as you're not too close. So in our lab, we do the ozone concentration measurement. So if you are away from the source, okay, 1 meter or 2 meters away, so the ozone concentration will decay to ambient level. So there's no really any threat for this health concern. Okay. Its efficiency depends on the system configuration. So that means that there are many factors to play. And so to design a system, you have to do this optimization. And so now I'm going to focus on how we apply this to enhance heat transfer. So as I mentioned, if we create this corona, so we actually introduce this electrical body force. So what are electrical body force? So electrical body force has 3 terms, okay? And the first term, from physics, we all know this is due to the Coulomb force. And the Coulomb force is a force acting on a charged particle. If a charged particle moving in the electrical field, it will experience a force. That's called Coulomb force. Right. So Coulomb force will apply, okay? And if the fluid is single phase, you probably only have this Coulomb force, okay? But if you're dealing with a 2-phase flow, then you have 2 additional terms, 2 additional force, and we call this 2 additional force called a polarization force, and this is due to epsilon here is electrical permittivity, okay? And because the electrical permittivity, if you have a 2-phase and the 2-phase have a different electrical permittivity, and so if you have this electric gradient, then it creates this polarization force. And if you are 2-phase, then because of density difference, okay, will also create this. So if you are 2-phase, then this force can change the interface shape. For my previous study, that we only focus on the single phase. And so because the electrical body force will come into play, okay, because electrical particle is going to drive the fluid. So we need to calculate this electrical body force accurately. If we don't calculate accurately, then your flow field, temperature field calculation will be all wrong, okay? And something, I don't know, some of you may have used this Fluent, or some of you may use this COMSOL, okay, all this commercial package. When you use a commercial package, all the commercial packages will claim say that, oh yes, we can do this, okay? But be careful. Okay, because we look into all this commercial package which they claim can do it. Actually, it's not, because what they do is they play some trick. I'll mention to you. Okay, that slide showing that what are the things that in electrical field. So in electrical field, if there's no ion, okay, then the electrical field will be controlled just by this Laplace equation. But because we generate this corona, so we have this charge. So we have to add that charge into the Laplace equation, so it will become Poisson equation. So that electrical, we call the charge density, is very important. And through this continuity, then we have this charge equation, okay? Okay, so these are the equations that I'm talking about for the electrical field. So if we don't generate corona, there's no ion, then there's no ion density, okay, charge density. So it will be a Laplace equation, all right? And because we create a corona, so we have a charge. So charge have a distribution, so we have this charge density. And so this equation coming from a reduced Maxwell equation, all right? And then if we combine with this continuity equation, and this is current, okay? So the current has 2 components. So one is due to this mobility, okay, ion mobility, and the other one is due to the convection, okay, convective. So if there's a flow, and the flow, okay, driven this charge, so we'll create the additional contribution to the current. So if we add this, and with the Maxwell wheel, then we come out with this charge distribution. And so in order to predict the electrical field, we need to solve this simultaneously, okay? And so we have to know this charge, okay, because the flow is driven by this charge, okay? And you can see this is a Poisson equation, but this one actually is what? The wave equation, okay? And so the wave, okay, the charge is distributed is from one point and downstream, okay? And so we need to know is the charge value at the source. And so that is something I mentioned that to do this, we have to know the value of the charge density at the emitting electron, okay? All this commercial package, okay, they do is that they apply empirical correlation, and so they use empirical correlation to assign the value at this emitting electron. Okay, and that is there's also this empirical constant. Okay, and so if you look at the literature, some people claim that they have a very good agreement with the numerical experiment. They are all false claims, because they can do, if they're using this commercial package, because this coefficient, okay, the user can play with and they try to force this agreement, right? And so because of that, we abandon use the commercial package. So we use the mechanism proposed by Yamamoto and the Volkov. And so in this case, what we do is that, okay, we let the experiment data to guide us. Okay, so what we do is start from the beginning. We will not apply voltage, and we solve the Laplace equation, assuming the charge density is 0. All right, and so we get the potential distribution. All right, and then we want to solve the charge density. So we initially guess a value for that, and then perform the calculation, iteration, and once it converges, then use the charge density, we calculate the current, okay, current deposit on the ground plate, and use that and compare with the experiment. Okay, experiment we can measure that current, and see these two. If they match, then we know this value we assume is correct. Then we can terminate this calculation. If not, then we have to go back and update this charge density at the wire and redo the calculation. Okay, and so this is for the electrical field part. So for the flow and the temperature part, so you all know that this is a two-dimensional equation, continuity and the momentum equation in terms of Navier-Stokes and the energy equation. The additional term is here, okay, because in this EHD study, then we have to add this electrical body force. So electrical body force is acting here, right? And if there's a large temperature difference, then we have to add the thermal buoyancy. And because there's an electrical charge in the fluid, so it will have this so-called Joule heating. Okay, so all this had to be considered. So I'm going to use this case. Okay, so to look at the heat transfer, so I'm going to look at is that if we have a channel, okay, forced convection, and we want to improve, okay, the heat transfer, so I'm going to put a wire in the middle of the channel, okay, single wire and two wire. And this idea is this. This is something that after my PhD, I was working with another professor that is working on electrostatic precipitation. So he wants to kind of predict how the efficiency of this electroprecipitator. So the professor asked me, see if I can predict the flow field. And so I do that, okay. And so here I'm going to define the Gamma parameter. So there's two Gamma parameter. One is a traditional Reynolds number. So Reynolds number here is defined based on the external flow, this in the flow. And the distance here, this is the gap between the channel is 2D. So using the 2D as a characteristic length. The other Reynolds number is based on this EHD. Okay, so this EHD, the velocity is based on the arm velocity. Okay, and so the reason is here we have a flow comes into the channel because a wire is going to generate corona wind. So corona wind will be issued from the wire to the ground. Okay, so there's another velocity. So we are looking at the interaction of flow field and the electrical field. So we have these two governing parameters. And so in this case, I've defined this a new parameter called EHD number. So this EHD number basic in physics is a ratio of inertial force, electrical force over inertial force. So because this Reynolds number is inertial force over viscous force, right? And the EHD Reynolds number is the electrical field, electrical force over viscous force. So the ratio of this is coming to EHD number. So EHD number is square. So that means that is square of these two ratio. All right. So this is the case if two wire, because it's symmetrical. So we can take the half domain. And this one is showing the charge density. So you can see the charge will be mostly on the wire, okay? And the charge will decay very fast from the source, okay? So far away from this wire, then it reduces to ambient, okay? And this one is the voltage. After doing the simulation, what we found is we apply at the full voltage, okay, 10 kilovolt, 12.5, 15, and 17.5. And plot this Reynolds number over this EHD number. So here, there's two symbol. One is open symbol, one is solid symbol. Because what we found in the flow field is that the flow will become unstable, okay? And so, depend on this EHD. Remember, EHD number defined as electrical force over inertial force. So that means that low EHD, that means the electrical field is very small. Okay, so mainly it's dominated by inertial force. So inertial force is dominate, so you can see this as all open symbol. So the flow is stable, steady, okay? And then with the increase of this EHD number, the flow will become oscillatory, okay? And because you have a 2, 4, 18 perpendicular, okay? And so this will become oscillatory until this electrical field increase. Okay, so electrical completely become dominant, then it suppress inertial, so the flow will be re-established, okay? And so this is something very interesting, but not many people observe. And because when I do this simulation, okay, there's one period of frustration, and that's something that is my advice for all of you graduate students. Because sometimes when we read the literature, okay, and we tend to assume that all the things published on the paper, on the journal are all correct, okay? And that's something is, you have to be aware. Not all the things you read on the journal are correct, okay? And so that's the thing is that when I do this simulation and I try to reproduce a paper's result, okay, from a famous researcher, and that is Yamamoto and Valkov. And in some case, I can reproduce, okay, there's the result exactly, but in other case, I cannot, okay, I cannot produce. And it is a very frustrating experience, and I don't know what happened. And later, I found out, okay, because the work was published in the very prestigious journal of Fluid Mechanics. So you will tend to say, okay, the paper in Journal of Fluid Mechanics, how can it be? Okay, how can it be wrong? Okay, it turned out, okay, there's a problem because in their work it presents this flow field, and you have to track until I trace back to the original source from Yamamoto's dissertation. Then there's one paragraph in his dissertation, okay, show the reason, okay, because Yamamoto, when he conducted this simulation, due to computational resources, he did not let the computer run through, okay. He terminated calculation at some point, given time. So he assumed that after running such long time, the flow was stable. And so what he presents is a partial result. And so after I find that, then I let my code run to at that time. If I run to that time, then I can completely produce the result. But because he terminated the computation prematurely, so he missed a very important physical phenomenon is like this, okay? Flow will be from a steady and transition to oscillatory. And that's something you may think, so what? Okay, Because that if the flow becomes oscillatory, it has a very important application because that can enhance heat transfer. Right? And so this is the case when we have a two-wire. For the two-wire case, it is more complicated. You can see the flow from the steady, go to this periodic motion, and then it will go to this non-periodic. So here, this part of the flow will be complete chaos. Okay, and this can be shown from this diagram. So here, this is a flow field, the different Reynolds number. Because the Reynolds number here are high, and so that means the inertial force is dominating. So the inertial force is going to suppress this electrical force. Okay, so that this is due to the interaction of corona wind and the primary flow. All right, and so if we plot the temperature, then you can see, okay, if there's no electrical field, then you should have a very smooth boundary layer. But because the electrical impingement, so you will disturb this temperature here. Okay, temperature, this boundary layer here. So, but this is still steady. But when we apply the case, okay, at the low Reynolds number, so that means the flow inertia is small compared with the electrical field. Okay, so in these two, they are the order of magnitude about the same, and so they are struggling for the dominance. Okay, so the flow become oscillatory. So I'd like you to pay attention to this generation of a cell, recirculated cell, and destruction of this. So let's focus on this recirculated cell. Okay, so that one you can see as the time goes, okay, it will grow. So you can see that the growth of the strength. If you look at the number of line, there's a string line, and then you move downstream, then you can see the strength reduce. Okay, strength reduce, and then you force out of the channel. Okay, but when you force out channel, another recirculated cell is recreated. So you can see this is a complete one cycle. If you look at the temperature field, this you can see the reason of this EHD enhancement because there's electrical field, so you can see create like wave-like, okay, wave-like disturbance to the this thermal boundary layer. So because electrical field and the oscillatory, it increase the mixing, okay, and so this heat transfer is increased. And so now if we plot this as a function, okay, this Nusselt number. So in order to evaluate the enhancement, so I use the ratio of a Nusselt number. So this is the Nusselt number with electrical field to the Nusselt number without electrical field. And so if there's no heat transfer enhancement, then this should be 1, right? And so now if we increase the EH number, remember EH number is the electrical force over the inertial force. So you can see with the increase of electrical field, then you can see the increase of heat transfer enhancement, right? And the solid simple is for the steady state. So solid state, I mean a steady state, there's an increase, but the enhancement is not as dramatic as the one with oscillatory. And so oscillatory case, I put this arrow bar, so that gives you the idea of oscillation. Okay, this is something. If you look at this magnitude, is a significant. Okay, if you look at all other heat transfer enhancement mechanism, usually will be what, 20%, 30%. But here you can see the enhancement is double. Okay, sometimes triple. Okay, that's a significant heat transfer enhancement. Right, and this is the one. If we use the more wire, okay, so you can see the enhancement is even further increased. So here I'm going to show you that how we apply this. All right, so I'm going to show you 3 videos. Okay, one is this one. So this one is here. This is a device that have been developed by a company in the U.S. Okay, so they use this for electronic cooling, and so this device is very small inside. So this is a dime. Okay, US is very small. Okay, and then here I use this they call it solid fan. So I'm going to create a smoke. Okay, so when they create a smoke and they pass through this and they turn on the voltage, then you will see the puff. Okay, the smoke will be accelerated, and then here this one is directly applied on top of a chip. And so when I play a video, please pay attention to this paper strip. So you will see the paper strip, okay, flattening. Okay, so let's see. Okay, you can see that all of a sudden those smoke that create the. Okay, when you turn on, you can see the puff. Okay, you can connect the electrode. Okay, and apply it and see the paper here. So that tells you that the mechanism of the wind that they created. And the same thing here, you can see that the paper is moving. Okay, so this is when we applied in the heat transfer enhancement, and with the same concept we can apply it to drying. Okay, this drying is when we applied in drying. Okay, for the study to show that this is effective in drying, so we conduct experiment in two cases. One is they dry at the ambient condition without electrical field, and the other one is under this electrical field. And also look at if we introduce the external flow, will that external flow help or hurt this drying? And so to evaluate this drying enhancement, so this is a result if we weight the sample. And so you can see as the time goes, the weight decreases. So that means that the water being taken out, and this is ambient, and this is the one with the electrical field. So the slope will represent is a drying rate. So if we take the slope, okay, ratio of this slope, then it will define. Okay, so here, in order to see the drying enhancement, so we define the Sherwood number. Sherwood number you can see is similar to a Maxwell number, but this is for mass transfer coefficient. All right, and then we are looking at treat the moisture as a concentration, and then we can define this mass transfer coefficient, and this drying is driven by the electrical field, so we use the EHD number to represent this electrical field. Here I'd like to show you the case. Okay, if we use 3 millimeter, because in order to quantify the result, okay, the drying, so I'm using a glass bead saturated with water, and try to look at this moisture removal rate. So this case is applied at the positive, and this is for negative. Okay, so what we see here is the drying ratio, okay, increase with the Reynolds number. So the Reynolds number is an indication of electrical field, so that's mean the increase of applied voltage, then drying is enhanced. So most of the case is linear. And this one is a performance. Performance is defined as the energy, okay, put it, okay, so that means that the mass of the moisture removed over the energy applied. So that means that for a given unit of energy, how much moisture you can take out. So from here you can see that this performance decrease with applied voltage. So that means that the low voltage, okay, it will become very effective. So means that the low voltage, the energy you put have a better result. So one thing is this, because the corona drying is on the surface, so like if the material is fully wetted, it will be very good because it remains at the surface. And so if you apply this to a partially wetted material, then it can be a problem because moisture will be deep from the deep inside. It's not at the surface. So the corona wind may not be as effective. So in this case, what we can do, if we have a waste heat, if you have a waste heat, you can apply it below. Okay, so use the waste heat to dry the moisture to the surface. And then then the corona wind can easily take the moisture from the surface and remove it. Okay, so this is another way to use in drying. All right, so in this case, so corona wind is effective on surface. Then we use the heater from the below to get the moisture out. And this is the result. Okay, if we don't use heater, so you can see that the slope is not as deep because as I mentioned, corona wind cannot penetrate. Okay, penetrating basic is remain on the surface. So now if we apply low heat, okay, and so you can see that gradually the slope increase. So get the moisture out to the surface. So these are the case if we try to find this correlation, because of all this data are very pretty much linear. So you can feel this a linear case. And so you may ask, how do we apply it, okay, for industrial application? So this is something one of a group student in my school, in their senior design, they designed this prototype. So basically, we use a convective valve, and the electrical field, electrical is produced by wire. So wire is perpendicular to this conveyor belt, and the belt itself is grounded. Okay, so we charge the wire on top, so it creates a corona wind, and the belt itself is grounded, and we use to dry this sand, and the result is presented in here. Okay, so you can see that this is the case. Okay, so the blue line is if without electrical field, and when we apply the different voltage, you can see the change of the slope. All right, so that shows this effectiveness in drying. So let me skip all the other and then come to the conclusion of heat transfer. So what we're seeing today is that the flow and the temperature field under influence of electrical field can become steady, periodic, and non-periodic, depend on the Reynolds number. Okay, and the heat transfer, as we see, that can be enhanced by this oscillatory flow. And in terms of drying, the same thing that we can see is that the drying enhancement will depend on the electrical field strength, okay, and the water level. Okay, so corona wind is particularly good for fully weighted material. If a partially weighted material, then it may require this using of auxiliary heater to get the moisture up to the surface. Okay, so that is the conclusion that we can make from this study. Okay, and I don't have enough time to show you that for the gas pumping, and the gas pumping is another area that you can investigate, because gas pumping that just by using this electrode, okay, without moving part, you can create the wind, and you can transfer this. So this is sort of like a quick overview of this electrical field application. This is a performance as I defined. So I'm using this as a heat transfer part. So compare that, say for example, you apply this in electronic cooling, okay? And this happened that we have data from the previous report. So they said compare this using the computer Feng, okay? And so this is the Feng size, and this is the flow that it can provide. So this is per watt, per unit watt energy put in. It can deliver this 1.79 liter per second of the volume flow rate. Okay, and so you can see that for this, okay, the most is about 4. All right, and but if you compare with the corona wind, So this one is that from our study of this, you can see the lowest is about 1 point something, okay? But the highest you can see that it's about 18. Yes, so you can see that for the same energy input, you can create much larger volume flow rate, okay? So this is in terms of energy, okay? So if you translate the energy into cost, then you can see the effect, okay? And for drying, it's not just the energy, but also other things like nutrition, okay? You can preserve those nutrition and you know, the texture of all this agricultural product, okay? Okay, thank you.